Hello everyone, myself Dr. Vijaykumar, Associate Professor, Department of Electronics and Communication Engineering, Aditya University. In today's session, we are going to solve the problems on random process stationarity. So at the end of this particular session, students will be able to learn two learning outcomes. One learning outcome is understanding the basic definition of random process and classification, and in learning outcome 2 we will apply the stationarity concepts in solving the real-time problems. So already we have seen all these topics in the previous sessions. Yet again we will recall all those things. So random process is a set of function or an ensemble defined with random variables on a sample space with a function of time. Simply, random process is a real function of sample space and time. It consists of two variables, one is sample space, other one is time. Next, classification of random process. Random process was classified into four types based on the parameters time and sample space. So, continuous random process, discrete random process, continuous random sequence, discrete random sequence. So, in a continuous random process and discrete random process, the sample space is continuous and time is continuous. We call it as continuous random process. Sample space is discrete, time is continuous, we call discrete random process. Continuous random sequence, this is if the time is discrete and sample space is continuous, we call continuous random sequence. Time is discrete, sample space is discrete, we call it as discrete random sequence. So, this classification already we have seen. Again, we will recall some concepts like ensemble averages and time averages. So, the statistical parameters mainly used in random process for analysis are mean, correlation, cross correlation, autocorrelation, cross correlation. If it is ensemble averages category, we compute the mean using this formula. If it is the category of time averages, we compute using this formula. The definition of stationarity. A random process is said to be stationary if all its statistical properties do not change with the time. Otherwise, we call it as non-stationary random process. So, in the previous slide, we have seen the stationarity parameters or statistical parameters mean, correlation and cross correlation. So, if these statistical parameters remains constant, we call it as stationary random process. Otherwise, we call it as non-stationary random process. There are different definitions for stationarity at several levels. We will see the definitions of stationarity at several levels. The first order stationary means the mean should be constant. If a random process is said to be second order stationary means the autocorrelation function must be a function of time difference, not on absolute time. If a random process is said to be wide sense stationary, it has to satisfy two conditions. Mean is constant and autocorrelation function must be a function of time difference. These both two conditions should be satisfied by the wide sense stationary random process. And one more stationarity is there, that is jointly wide sense stationary. So, generally this concept is valid for two different random process x of t and y of t. So, the random process of x of t mean should be constant and the mean of random process y also should be constant. Along with that, the cross correlation function of two random processes x of t and y of t must be a function of time difference. So, all these three conditions must be satisfied, then only we can conclude it is a jointly wide sense stationary random process. And one more definition of stationarity is there, strict sense stationary. If an nth order density function of a random process is not changing with the time, we call it as nth order strict sense stationary. If it is stationary up to kth order, we call it as kth order strict sense stationary random process. Next, we will see the problems related to the stationarity concept. So, a problem is given, they are asking us to verify whether the random process is wide sense stationary or not. So, random process is given x of t is equal to sin omega t plus phi, and phi is a uniform random variable defined over the interval 0, 2 pi. Now, we need to verify whether it is wide sense stationary or not. So, the conditions we need to verify for wide sense stationary random process are mean should be constant and autocorrelation must be a function of time difference. So, we need to compute two statistical parameters and based on their values we need to verify whether the conditions are satisfied or not. If the conditions are well satisfied, then we can conclude it is a wide sense stationary random process. So, given phi is a uniformly distributed random variable, f phi of phi is 1 by b minus a, uniform random variable 1 by 2 pi minus 0, 1 by 2 pi over the limit 0 to 2 pi. And we will compute first the mean value. The mean value is computed using the formula expectation of t 1 by t minus t to t x of t dt. So, based on that formula 1 by 2 pi 0 to 2 pi sin omega t plus phi. The integration of sin will be a cos function, cos omega t plus phi. We know that the cos 2 pi minus cos 0, 1 minus 1, we will get 0. So, the mean is a constant value. The first condition is well satisfied. Next, we will verify the second condition. We will compute the autocorrelation function for the given random process. The formula for computing the autocorrelation is expectation of x of t plus tau. In place of t, I need to substitute t plus tau. So, sin A, sin B can be written as cos A minus B minus cos A plus B divided by 2. So, applying that formula, expectation of cos omega t minus cos 2 omega t plus omega tau plus 2 phi. Expectation of cos t, expectation of this function we need to compute. So, we know that the cos omega tau, actually this is cos omega tau, this is expectation of tau. So, expectation of constant is constant, expectation of c is c. So, we will get 1 by 2 cos omega t, and when we do compute the expectation for this function in a similar manner, I will get sin in terms of sin 2 pi minus sin 0, we will get overall answer 0. So, the cross correlation function is a function of time difference, but not on absolute time. So, the autocorrelation function condition is satisfied. Clearly, it is a function of time difference, but not on absolute time, and the expectation of the random process is constant. Both conditions are satisfied. Then we can conclude clearly this is a White's and stationary random process. So, next one more problem we will see related to the statistical parameters computation, mean and autocorrelation function. If a random process x of t is given, and here also it is uniformly distributed random variable. So, fa of a will be 1 by a over the limit 0 less than a less than 1. Okay. So, this is the uniform density function for the given parameters. Now, we need to compute the statistical parameter mean. Expectation of x of t, expectation of a is a into fa of a, fa of a is 1 by a. So, 1 by a is substituted. So, a square by 2, so 1 by 1 minus 0, 1 by 1 minus 0, this is 1. A integration is a square by 2, substituting the limits 1 by 2. So, the mean value we will get is 1 by 2. In a similar manner, we need to compute the autocorrelation function, expectation of x of t into x of t plus tau. X of t is a, x of t plus tau is a, expectation of a square. So, a square into fa of a dA, fa of a is 1. A square integration is a cube by 3, substituting the limits we will get 1 by 3. So, the mean and autocorrelation are computed for the given random process. Next, we will see the problem to verify the stationarity of second order. So, how do we verify the stationarity of second order? We need to compute the autocorrelation function. Autocorrelation function must be a function of time difference. This is the condition to be satisfied. Rxx of t comma t plus tau must be equal to Rxx of tau. This condition to be satisfied. So, given the conditions, expect a and b are independent random variables and 0 mean and equal standard deviation. So, both I will say both are equal to sigma square. Now, expectation of x of t, expectation of a sin t plus b cos t, a is a constant, expectation of a will be same, expectation of sin t plus expectation of b into expectation of cos t. Given expectation of a is 0, expectation of b is 0, 0 into sin t plus 0 into cos t, the answer will be 0. Next, we will compute the autocorrelation function, expectation of x of t into x of t plus tau, substituting the limits and multiplying sin t into sin t plus tau, expectation of ab cos t sin t plus tau, expectation of ab sin t cos t plus tau, expectation of b square cos t plus tau. Given the variance is constant, which is equal to sigma square, we know the relation variance is equal to expectation of x square minus expectation of x whole square. Since the mean values are 0, expectation of x square will be sigma square. In a similar manner, expectation of y square also will be sigma square. So, I will replace expectation of a square and expectation of b square with sigma square. Next, expectation of ab. Since both are independent random variables, expectation of ab is equal to expectation of a into expectation of b for independent random variables. Given e of a is 0, e of b is 0, overall it will be 0. So, expectation of ab terms will vanish in the expression. Now, sigma square cos t plus tau plus sigma square sin t plus tau. Sigma square I will take common. This can be written as cos of a minus b, cos of a minus b. So, doing the t cancels out, it will get sigma square cos tau. So, clearly the autocorrelation function is a function of time difference. So, it will be a stationarity of second order. The condition is satisfied. Now, we will see the problem related to the jointly Whiteson stationary random process. So, a random process is said to be jointly Whiteson stationary. We need to verify three conditions. Expectation of x of t must be constant, expectation of y should be constant, and cross correlation function must be a function of time difference. So, all these three conditions are satisfied, we can conclude it is jointly Whiteson stationary. Given a random process x of t and one more random process is defined y of t, which are related in the expression y of t is equal to x square of t. We need to verify whether x of t and y of t are Whiteson stationary, and also we need to verify the condition whether they are jointly Whiteson stationary or not. So, given theta is a uniform random variable, for a uniform random variable f theta of theta will be 1 by b minus a, that is 1 by pi minus pi, and limits of theta will be minus pi to pi. So, this is the uniform random variable density function. Now, we need to compute the expectation of x of t. So, x of t is a into sin omega t plus t. So, expectation of a is a constant I am bringing outside. Expectation of sin omega t, if you compute, what we will get, cos 2 pi cos pi minus of cos minus pi. Cos pi is minus 1, cos of minus pi is again minus 1, minus 1 plus 1 we will get 0. Expectation of x of t, what we will get, 0. Similarly, expectation of y of t we need to compute. What is y of t? X square of t. Y of t is x square of t. X square of t means a square sin square omega t plus t. We can write sin square theta is 1 minus cos 2 theta by 2. Now, expectation of 1 is 1 a square by 2 minus a square by 2, expectation of cos 2 omega t plus theta. So, the integration of this function we will get sin pi minus of minus sin pi is 0, sin minus pi is 0. So, this term will become 0. So, the expectation of y of t what we will get is a square by 2. Next, we need to compute the cross correlation function Rxy of cross correlation. First we are computing the autocorrelation, we will get a square by 2 cos omega tau, and similarly expectation Ryy of tau we are calculating, we will get this one. So, y of t also Whiteson stationary, x of t is Whiteson stationary. So, both conditions are satisfied. So, clearly we can conclude that x of t and y of t are jointly Whiteson stationary random process. Here we are asked to compute the covariance. The formula of covariance is Rxy minus x bar into y bar. So, x bar is the mean value of x, y bar is the mean value of y. If it is the same function, covariance of x is equal to Rxx minus x bar whole square. We know that expectation of x of t already we computed in the previous problems, we will get 0, and Rxx we will get 1 by 2 cos omega tau. So, 1 by 2 cos omega tau. So, covariance will be 1 by 2 cos omega tau minus 0 square. We will get 1 by 2 cos omega tau. So, this is the covariance answer. Covariance and autocorrelation are same because here the mean is 0. Expectation of x of t is 0. So, we will see one more problem which is related to two different random variables. They are related with the relation y is equal to integral 0 to 2 x of t dt. Given the mean value of random process x of t as 3, autocorrelation as 9 plus 2e e power minus 2 tau. So, we need to compute the mean and variance for the newly formed random variable y, which is the integration of x of t over the limit 0 to 2. So, the expectation of y will be expectation of this one. So, integration of 0 to the expectation of x of t. Expectation of x of t is 3, I am substituting 3. So, integration of dt is t. So, substituting the limits 3 into 2 minus 0, I will get 6. Expectation of y is 6. Before computing the variance, we know that the variance is related as expectation of y square minus expectation of y whole square. So, we need to compute the mean square value of y, expectation of y square. Now, here expectation of x of t into x of u, it looks like a correlation function rxx of t minus u. So, rxx of t is given, I am substituting the limits, and for 36 dt, if you do 36 in 9 into 4, 36 we will get, I am bringing outside 2 into limits for this function, we will get 36 plus 2 into 1 plus e power minus 2 plus e power minus 2. We will get overall answer 40 plus 4e power minus 2. So, now finally we need to compute the variance, expectation of y square minus expectation of y whole square, 40 plus 4e power minus 2 minus 6 square. So, 4 plus 4 is power minus 2. So, if you separate 4, 1 plus e power minus 2, the variance is 4 into 1 plus e power minus 2. So, in this session what we have done is, we have defined the random process and we recall the definition of random process and we classified the random process, and we have defined different levels of stationarity like first order stationarity, second order stationarity, Whiteson stationary, jointly Whiteson stationary, Stichtson stationary, and we have solved the problems, real time problems related to the stationarity concept in the random process. Thank you.